Good morning, ladies and gentlemen, wherever you are in the world, or is it good afternoon or good evening? I'm not sure where people are calling in from. My name is Tim Collins and I'm the Secretary General of the International Stainless Steel Forum, based in Brussels in Central Europe. Welcome, everybody. Thank you very much for joining our second webinar in our trilogy of protecting our people. And today we're going to talk about, or I'm going to talk about, coastal structures. Now, a few housekeeping things before we start. The presentation will be sent out to everybody who's registered for the session today, so you don't necessarily have to worry about taking notes. So everybody will get the presentation. The presentation slides and my narrative will be recorded and posted to YouTube. So again, there's a chance to re-watch everything with the narrative, so you can pick up on issues that maybe you'd like to just revisit. Any questions, I would ask that people pose them via the chat facility. We will not have time to answer all questions at the end of the session. However, all questions pitched via the chat facility will be answered, if not during the live session today, with an email response. So there will be no questions that are missed. And I'd like to sort of just let everybody know that, you know, if you've got a question, please pitch it. And even if the question comes after the webinars, that's fine. My email address is at the bottom of the opening screen. I'm today ably assisted by Joe Class from the ISSF as well. And Joe will be making sure that I don't go too off-piste, so to speak, and we keep time going. I expect the presentation to run for about 45 minutes, leaving 15 minutes for questions at the end. And as I said, we will get to all questions either during the session or via email. So if everybody's sitting comfortably, I will begin. So let me just get rid of this banner on the screen. Okay, so we've quite a few topics to get through today, about 10 in total. Some are relatively short. I'm not going to read out the list because I'm sure everybody out there is capable of looking through that. And we'll highlight each section as we move through the agenda today. So in terms of our introduction, I'm just going to try and set the scene before we go and look at global mean sea level rises and what that actually means for us. So in terms of introducing this topic, there are a few things that we know, or perhaps we should know if we don't. I think everybody is probably aware that the global mean sea level is rising, and this data is absolutely known and certain, and the pattern is there, and I'll show some information on that shortly. It's not just rising though, it's actually accelerating, and this is understood with a high degree of confidence. And really there are two main features. It's glacier melting and contributions from ice sheets melting, and these are the dominant two sources. Again, this is understood and known with a very high degree of confidence. However, we need to link all these developments to the United Nations Sustainable Development Goals. And looking at what's known as climate resilient development pathways, this requires some serious effort to contain sea level rises, because you can't just switch these things off. And when I get to some of the charts that actually show what's happened historically up to 2020, and then how that is likely to look in the future, you'll probably see that we do need to take some significant efforts. Now, through the course of this webinar, we're going to look at a number of approaches for protecting our coastlines. But there are two key features or two key approaches that are really worth considering and need to be considered. That's hard protection, building a barrier, and what's known as building advance, building out into the sea. And these are two arguably economically efficient approaches because you deliver protection, or you avoid land being swallowed up. And for urban settings, this is well understood and well used. However, because you're offering protection, taking a long-term view, actually you don't see the impact that potentially could come later. So there is a risk associated with hard protection if it's not really thought about in a long-term setting. But also, there's the concept of equity concerns here, or the sort of difference between the rich and the poor nations. And the people that are in the most vulnerable areas are probably, in many cases, the poorest nations. So we have another risk that responses to sea level rises can spark or compound social conflict. And we have to be mindful of that, that it's not just the developed nations that are going to suffer in this case. So that's my scene setter for the introduction. I'd now like to move on and talk about global mean sea level rises and illustrate what we're actually facing. So what do we know? So here is some data from the International Panel on Climate Change showing the level of sea level rise over some interesting time blocks. What you can see from those numbers is that since the turn of the 1900s, that increase has been rising, slow at first, but it's accelerating without a doubt. And the dominant cause is something known as anthropogenic forcing. So that's what we do as people. That's the influence we exert on habitats and environments. So the responsibility sits with us, and that's been more and more prevalent since 1970, essentially. The worrying thing is when you start to look at the trend, over the next 80 years, looking at different pathways, and there are many of these representative concentration pathways that have been described, the average sea level rise is going to sit at around 0.6 of a metre, somewhere between 0.43 if we allow the global mean increase in temperature to not exceed 2 degrees centigrade, or closer to a metre if we continue on the path that we're already on. This is the 6-degree increase in global mean temperature scenario. So there's a range of possibilities, but none of them are good, and there's different pathways in the midst of these two extremes that I'm showing at the minute. So this table just summarizes very simply the same data from the previous table, so I'm not going to go over and describe that, but it puts things in simple context for reference. But also it's worth reflecting on, over the period 1980 to 2015, worldwide catastrophic events and how they've changed. And this chart shows, for specified years, of which there are 5 in this chart, the different number of serious events, whether they be meteorological, hydrological, or climatological. And you've got the description of the bottom of what they actually mean. But what is absolutely scary is the percentage change in the number of these events in these year intervals that we're showing here. So approaching a 70% increase in total on these total combination of events. And of course, hydrological events, which is interesting for this particular webinar, has gone up almost 80%. I don't yet have the data for 2020, so I was not able to show that. But this is quite frightening. And it's also known, and this is Red Cross data, that approximately every $1 spent on reducing the risks from disasters will save around $7 of clearing up damages later. So there's a massive impact. It's a 7-to-1 impact, and that's an important message to take forwards. So let's have a look at global mean sea level rises. So this is the actual events from 1900 up to 2020, shown on the left-hand side in the actual section, and then the forecast of how it's going. And this is mean sea level rises. So of course there will be some variation around this, but you can see the trend. And if that trend continues, that's quite worrying. Now, what's really interesting is when you put against that a note, just before I move on, the scale. This goes from 0 to 1.5 meters, this scale. So the next 80 years, we're going to be pushing upwards towards a meter if we change nothing. This is based on the 6 degrees scenario. If we now put extreme rises on there, you see how the blue dotted line now looks. And these are the variations that we see naturally. So these things do occur. They're not there day in, day out, but these extreme rises will affect different parts of the world at different times. So we have to work out, or we have to consider, that the average, the mean sea level rise is not the true picture. And then, and this is the same scale, 0 to 1.5 meters. What I'm now going to do is impose the average tsunami position on this. And now this is a different scale, 0 to 7 meters. And you can see the average tsunami line, the dotted red line, is frightening. So this puts in context, whilst we are facing some significant average sea level rises, there are some disastrous effects that we just cannot avoid. And doing nothing and having a heavy reliance on fossil fuels is only going to make this picture look at its bleakest, I think. But it's also worth reflecting on, you know, some other ways of approaching this. So this is data from the US Atlantic coast, and this looks at coastal flood days going back to the 1950s, and this is in sort of broadly 10-year blocks up to 2014. And this chart looks at coastal flood days and their basic cause. Are they natural effects, or are they human caused? Are they caused by anthropogenic forcing? And what's interesting is, whilst both of those blocks in the graph from the mid-50s up to the more present time are increasing, the rate of human-caused floods has gone up massively, from an average of 1 a month in the mid-50s to mid-60s to 18 per month. And this is only the US Atlantic coast. So this is quite again, a scary and compelling picture. This shows the change of what's happening. Now, these are transient floods. These are not floods that are there all the time. But this is a really scary indication of how things are changing and supports the trend we're seeing on the other graphs about mean sea level rises and tsunami levels. And just to emphasize, when we talk human caused, these are features arising from industrialization, the increase in mass urbanization, poor river management, deforestation, and loss of floodplains. So there's a lot of things we're doing to drive our societal needs that are creating these problems. Okay, so that looks at sea level rises. We're now going to quickly describe the coastline environment. So this is just a few bullet points as sort of key features of the coastline environment. And I think some of these will be well known to people and some probably just important reminders. So we know, due to the chloride content in seawater, we have corrosive conditions. I think everybody would accept that. We know that along coastlines, erosion constantly occurs, but it is accelerating as well. So with the sea level rises, accelerated erosion. We know that we've got an increasing average and extreme seawater levels and an increasing frequency and severity of the extreme events. But then we have to sort of balance that up, about reminding ourselves that coastlines provide a base for some very important economies. I would describe them as a societal people magnet. People like to go to coasts. We can't change that, that won't change. But also, we are responsible for using coastlines as a dumping ground for undesirable wastes. And there's many, many experiences that we will all remember over the history that we've experienced of some undesirable effects. But we should equally remember that coastlines are highly sensitive to the impact or the unwanted impacts, I should say, of carbon intensive, both coastal and off coastal industries. And they then take a long time to recover. So we've been doing some damage to our coastline for considerable amounts of time. And we already know that coral reefs, for example, are highly bleached, and that will take huge amounts of time to recover. So the first question I'm going to pose is, can we really preserve these idyllic coastal settings, look after the coastline economies, support the coastal ecosystems, provide safe holiday environments? We've caused, as a race, lots of devastation. I think we all have to take personal and collective responsibility for that. But a question I'd like to pose here is, if we lived a lot longer, if we lived for 250 years on average, would we actually have thought differently? Because we'd then be living with the consequences of our actions. And I think it's important to have that thought in our minds, because that will change what we do in the future. So I'd now look to move on to approaches to coastal defences. So a couple of provocative statements in this slide. I would argue that coastal defences, or our approaches to them, are often simplistic and based on old style thinking. We're taught often by people who are experienced in this, and actually bringing in new ideas takes a bit of time. I would equally argue that the corrosive effects of the sea are not thoroughly understood. Certainly when you're talking about different materials and composite structures, you're into some complicated corrosion features. I would also say that the erosive effects of the environment are not thoroughly understood, because they are dynamic and we now know they're worsening. We still have a short-term sort of piece of thinking in many of our minds, and I've been equally guilty of that. And that's driven often by installation costs and material costs, considered well before life cycle thinking. But we have to recognise, and we should recognise, that life cycle costing is becoming more important. And from a position of finance companies, they are wanting to see this piece of thinking in new projects. We equally know that insurance costs are not yet fully aligned to resilient and sustainable structures, but that's starting to change. So there's a lot of features here that we need to consider and reflect on some important changes in our thinking that we all should be starting to adopt. But what would happen if we just chose to do nothing and carry on as we are? For many of us, we have nice and comfortable lifestyles. But this is just an example of a handful of cities, 6 cities, and there are many more than this, that would disappear or partially disappear within the next 80 years. And this is frightening. This is not one part of the world, this is all over the world. And we could populate this picture with up to 100 cities quite easily. So this is just to reflect, doing nothing is not really a choice we have. So we have to do something. And I think we have to decarbonise our society. That's understood, and I think pretty much well known. We equally have to protect our people and our land. So we know that sea levels are rising. If we can't protect our people and we can't protect our land, we won't have a basis for an agricultural economy. We have to protect the other economies that exist, and we have to allow our ecosystems to recover, because that's important in controlling things like the frequency and severity of floods, sea level rises, etc. But it's slower, but we have to give them time to recover. Therefore, I would argue, we need to think long term. We need to future-proof our facilities and installations. We have to think about using sustainable materials and stop using fossil fuels. We will, in the short term, have to use carbon capture schemes and recreate some carbon dioxide sponges, whether that be through new forests or other natural installations, or putting CO2 into caverns below the ground. And we have to think about zero maintenance. This notion of having industries based around regular maintenance and firefighting is something we do need to get away from. So now let's focus on coastal defences, and that's a classic image of a typical coastal defence, and you can already see on the vertical concrete structure to the right, some of the sort of sea salt degradation starting to feature, and whilst it's not extensive, you've got the first signs of something going on there. So we've got a few options. This is not an exhaustive list. This is just 6 easy to understand options. I've talked about hard protection, building a physical structure, and that accommodates many meters of sea level rise because you can build these things high, but it doesn't come cheaply. It's relatively high cost but effective. Coastal advance, building out into the sea, again can accommodate many meters of sea level rise, but that's even more high cost. So that's really reserved for very specific needs and applications. We can also do things to conserve and restore our wetlands, and that's really good to do. However, it doesn't accommodate many meters of sea level rise per year. It's only about 10 millimeters per year, but it is additive. So we shouldn't just ignore it, but it's not going to solve all the problems, particularly when we're looking at extreme situations. We can look at sediment-based protection, and that's okay if the sediment sources are available. We have to recognise we're here robbing something to pay something else. So the source environment where the sediment comes from will be destroyed. So interesting option, but not always completely desirable. We can look at conservation and restoration of our coral reefs. Again, that's interesting and I would argue important, but it doesn't accommodate too much sea level rise per year, just around 5 millimeters. And then of course we can accept that the sea is going to swallow up land and move people, relocate people. The downside of that is we're already looking at a significant uplift in mass urbanization over the next 30 years, and this will just add to it, and it will result in a loss of livelihood. So there's always a consequence to doing some of these things. But I would argue they're the main sort of 6 areas to focus on. Now, within what I'm going to talk about next, I'm obviously not going to talk about all of those things, but we are going to look at different protection mechanisms or hard protections. So in the area of hard protection, what we're going to start looking at is physical barriers, obvious things. And I've got 2 examples here to illustrate. The first one is the Bayonne Breakwater in France, which was protecting a harbour in France, and there were a lot of ships sadly grounded on this breakwater due to the very rough seas. So the rough seas necessitated the protection, but it was also problematic as well. And this photograph shows a nice example. So there's this breakwater. You can see a photograph of it on the right, and a nice crack running along the running surface of the breakwater. This was owned by Region Aquitaine, protects the port area, as I've said, and the asset was subjected to extreme seas. So what we had was a situation with cracks on the running face of the breakwater itself, where mobile plant went up and down, but also cavities below the surface and of a significant size. And a repair was needed to this breakwater. The requirement was a service life of more than 50 years with 0 future maintenance. But in order to achieve that, the owners knew they needed to seek some technical assistance. However, the project manager who was appointed to this project understood the benefits of stainless steels via the Progresso Pier case, which I will illustrate towards the end of this presentation, where we get to life cycle costing. So there was some understanding that there was a material out there that could assist with this repair. And now in the diagram, you've got a slice through the breakwater with the sea out to the right, the river to the left, and the shape of the breakwater and the component parts illustrated in the diagram. And for the repair, 2304 duplex stainless steel reinforcing bar was chosen for the project, really for 2 main reasons: a high strength, so a yield strength of greater than 650 megapascals, and excellent corrosion resistance. The pitting resistance equivalent number was above the seawater threshold, and that's important because in chloride rich environments, pitting resistance is the main form of corrosion, the main corrosion mechanism. So with this solution, we had a material that could not corrode in the environment, but also because of its high yield strength, it meant that a much lower tonnage of stainless steel was needed compared to carbon steel if that had been chosen again. And the original solution was with carbon steel. So there was good reason for choosing a stainless steel here. It ultimately led to a very sustainable solution. Just as carbon steel is made mainly from recycled steels in rebar cases, so is stainless. So there's no difference there. It's both part of the sort of circular economy, but a real benefit from choosing the stainless option. And we would expect the service life to be closer to 100 years with really minimal maintenance. The next example I'd like to look at moves to the UK, and this is a North Norfolk coastal location, a holiday location known as Cromer. And there you can see in the diagram towards the bottom of the picture a part of the seawall that runs along the sea front at Cromer itself. And this is an important seaside town, as I've said. Over many years, they've managed to limit the erosive power of the North Sea by an extensive seawall. You've seen a part of that, and timber groins that were periodically repaired, and they came out at 90 degrees from the seawall into the sea. But back in 2013, Cromer, not just Cromer, but this part of the UK was subject to a major storm, and significant repairs were needed to the seawall. So what was required, that the existing level of defence for the town above the coastal area was required, withstand 100 years of predicted sea level rise. So this is a great example of where sea level rises were being understood, and there was a requirement to say, hey, we have to think long term here, which was great to see. And again, 2304 duplex stainless steel was used as rebar to support these objectives. We see some other similarities between this and the Bayonne Breakwater, where less replacement concrete was required to cover them carbon steel would have needed, because carbon steel will obviously corrode in this environment and duplex stainless will not, and the additional strength brings additional benefits. And we know that we're going to let this revised or rebuilt seawall survive for 100 years, even with extreme events from the chloride-rich North Sea. So this is just a sort of mirror, really, of the work done in France. Same sorts of requirements, same choice of materials, combination of stainless steel rebar and concrete. So I'd now like to move on and consider extreme protection. And I'll illustrate this again with one case. And now we're going to move to Japan to look at extreme protection. Here's an example of a huge flood barrier. But if we think back to 2011, I think many people will remember the tsunami that hit Japan. And this example focuses on Miyako City. And you can see some of the devastation in this photograph caused by the tsunami that sadly hit. So in 2011, Miyako City was hit by a tsunami that was around 10 meters in height. The sad thing was that more than 500 people died, and almost a quarter of the housing of the city sustained significant damage. So this is a real example where an extreme event causes a huge loss of life and major damage to the coastal city. So to cut to the chase here, the response to that was to build a significant seawall, 9 meters high, and 20 lock gates as well along that section of the coast. Again, this was a case where duplex stainless steel was chosen for the lock gates, and previously they'd worked with an aluminium alloy, so the increased strength of a duplex stainless steel allowed an overall weight reduction per gate, which was really prized, given that you have to remember aluminium is a very light alloy, or aluminium alloys are very light. The construction cost by designing and choosing a stainless steel, or designing with and choosing a stainless steel, was reduced compared to previous designs. There was a huge step up in corrosion resistance, and the design that was chosen and the height that was chosen allowed this structure to withstand the pressure of 10-meter high tsunami waves. So some would say, hey, is it high enough? It's one of those things that we don't know, but certainly there is the opportunity to add to height on things like the gates and the wall. So it's not a closed position where this can't be enhanced if that is required. But for what they'd suffered as an extreme, this was certainly a good solution. And here's a photograph of one of the constructed lock gates. You can see, when you compare it to the humans at the bottom of the picture, just the sheer size of the thing is enormous, but very impressive to sort of safeguard a city. And this is the sort of thing we will have to think about seriously. Okay, so now I'm going to move on to something a little different and talk about infrastructure crossings. And in this section, we're looking at essentially bridges that cross seaways. And many people will say, hey, why is this a coastal defense thing? What we have to remember in our environment are things like people flow and trade flows that we can't just switch off to allow our cities to operate as they do, to allow businesses to be successful, to allow international trade to occur in a successful and streamlined manner. We need bridges, and bridges across significant seaways are really important. And I've listed 3 examples. On the left, the Stonecutters Bridge in Hong Kong, the Sheikh Jaber Causeway, that's not the full name, that's just the abbreviated name in Kuwait, and the Champlain Bridge in Canada. And I'd like for this example to focus on the Samuel de Champlain Bridge in Canada. And there's a beautiful picture of the bridge in all its glory. But let's just put this in context. So this is almost a 3.5 kilometre long bridge over the St. Lawrence Seaway in Montreal. It's used by in excess of 50 million vehicles per year, including way above 200,000 buses. There are 11 million transit users per week, and of those, 2/3 of them are commuters. So this is why these sorts of structures are important. And also it supports $20 billion of trade between Canada and the US each year. There was a bridge that was built back in 1962, and this was not designed for either the current traffic needs of when this was looked at in the early 2010s and the future traffic needs either. And that structure was suffering from corrosion of the structure and concrete degradation caused by both the seawater and de-icing salts used because of the extreme weather conditions on the St. Lawrence Seaway. And the degradation of concrete came from volume expansion of the rusting steel inside the concrete, because corroding steel increases in volume due to the volumetric expansion when iron combines with oxygen. And that also changes the pH as you get carbonation of the structure, which causes further degradation of the concrete. So that combination of using or having a seawater environment, using de-icing salts, a lot of traffic over the bridge causes a lot of problems when you have a rusting product inside the concrete. So here, the client was the federal government of Canada. I think this is an interesting reflection, that this was something driven by the government. They saw a true need. But the project was an alliance contract, so it's a public-private partnership. The project cost was 4.5 billion Canadian dollars. I think the original budget was only slightly below that, it's about 4.2 billion. So the scope creep in terms of cost was very little. The key requirements were at least 125 years of useful life and selecting materials and components with the lowest life cycle cost. And that's important to reflect on. These people were really thinking about life cycle costing. And I've talked about the harsh weather conditions and extensive use of de-icing salts. This is an extreme environment up there on the St. Lawrence Seaway. Construction ran over 4 years, 2015 to 2019, and stainless steel 2304 duplex reinforcing bar was selected. And this was a significant project, 15,000 tons. So very significant use of stainless steels in a single project. So why, for this project, do they choose stainless? Well, it was one of the few materials that was certain to operate for over 100 years with virtually minimal or zero maintenance. The lean duplex stainless steel was chosen because it was that, again, that combination of really good corrosion resistance and high strength, particularly with respect to chloride corrosion, as I've mentioned. And it won't require any challenging maintenance regimes. You know, it's important to reflect on the old bridge, the old structure built in 1962, operated for 57 years, but every year it was expensive to maintain. And that's not something we necessarily want. We want to build with a sort of fit and forget mentality in our heads. So I'd now like to look at, quite briefly, some other forms of protection. And here's a lovely photograph of what can go wrong as coastal erosion takes place. And those, I guess they're apartments or holiday homes, are perilously close to the edge of the cliff, which is not a nice place to be sitting in. So we'll look at two features here, something known as gabions. It may not be a common term to everybody, but these are essentially wire cages containing rocks. And you can see the photograph on the right, a terrace made out of these wire cages that protects a high landmass behind it. And the cages, once they're sort of filled with rocks, can be built rather like Lego bricks into a protective wall, but obviously a bit more substantial than Lego bricks. And the wall itself quickly dissipates tidal energy. So it acts as a barrier, but in a different way. It's taking energy out of the onrush of water and waves. So it protects effectively high coastline areas, as shown here, where you've got arable land. And one of the things you have to remember is, because these cages are built from a wire structure, in essence, they're subject to both erosion and corrosion. The rocks move around in the cages. When they hit with the seawater, they'll settle over time. So choosing material that is coated, something like a galvanized steel product, will actually, you'll lose the zinc coating through erosion primarily. So you need to choose a material for these applications that is going to hold the rocks in place for a long time. And again, stainless steel wire is the optimum choice, because then it's a fit and forget feature. One of the other areas we need to consider is cliff mesh as well, in order to protect some of our cliff faces, particularly with the erosion effects which are exacerbated by extreme weather events we see now. That looking at wire mesh using stainless steel and rock bolts to secure those meshes in place becomes, again, the optimal choice, I would argue. You've got the same features going on if you choose a galvanized steel wire. You will lose the zinc coating, and something that's not protected, even if you think about epoxy coatings, the erosion will wear away the coating and you'll be into a mesh that fails. So I would argue, first and foremost, that whilst stainless may be a little more expensive up front, the notion of let's simply fit and forget has a lot of benefits. As extreme weather increases, the last thing you want to be doing is sending people up cliff faces, refixing mesh onto these cliff faces. So we have to think about, is maintenance in the future even going to be safe, not just about the choice of materials up front. So now I'd like to sort of, as I get towards the end of this presentation, and we're running perfectly to time, which is good, just look at life cycle costing in a comparative manner. And I'm going to illustrate this with the Progresso piers, which I talked about earlier in the presentation. And back in 1941, a large pier or causeway was built using 316L stainless steel rebar. And this was an very early use of stainless rebar. And you have a picture just below showing that causeway in modern times, still perfectly intact on the right. And then much later, 1969, an additional pier was built using carbon steel rebar. And you see now the relative comparison below. So after 40 years in service, the carbon steel rebar pier had all but disappeared. You just have a few stanchions left, and the 1941 pier still intact and looks good. So this is a really wonderful example of where material choice, and I know the smaller pier built in 1969 was not built with the same purpose in mind, but if we're thinking about trade routes and climate change and extreme sea level rises, we have to think about building with materials that will last more than our lifetimes. We have to think the 250-year lifetime concept. But how does that look in sort of comparative financial terms? So this is a very simple diagram illustrating the life cycle costs of the carbon steel pier on the left, built in 1969. I'll show the stainless equivalent. And basically you have four straight components: the cost of acquiring the materials for the project, the cost of installation, any costs associated with maintenance, and then any income at the end of life from items that you can get scrap value for or reuse and sell in some way. So you've got three additive components and then a financial benefit at the end. So you can see this will be a comparative scale. We're not using actual numbers, but this has been derived from actual numbers. So you can see here the sort of build up of those life cycle costs of that structure. And then we put alongside it the 1941 built life cycle costs. And there's no doubt you pay more when you've got stainless steel in the structure. So the acquisition costs of the material are higher. The installation costs working with stainless is a little more tricky, are slightly higher, but then everything changes. So the maintenance costs are incredibly low, and the income at the end of life, when it occurs, will be relatively modest too, because you've not had to progressively replace things. So this shows that really you have something of the order of a 20% difference or slightly more than that in terms of life cycle costs when choosing the right materials for the application and thinking long term. And what's important here is taking away the disruption that maintenance brings. And I know this is a slightly different example, but we shouldn't ever forget that when we have maintenance work on things like bridges and other structures in our road network, the CO2 emissions from standing traffic represents about 1% of our total global CO2 emissions every year. So it's not insignificant that we continue to pollute our environment when we're repairing things. We shouldn't ever forget that. So I'd now like to sort of draw this to a close with a summary page and a conclusions page. So I think it's fair to say the next 80 years are critical for our coastlines, and we've got to think not just about the lives we're going to enjoy, but our children and our children's children. The historical evidence about mean sea level rises and extreme sea level rises is compelling, and natural protection will not save us. I think it's equally fair to say the 2-degree scenario from the Paris Agreement is looking unlikely, so that will bring more extreme weather. And therefore, we have to recognise that hard coastal protection solutions will be necessary. We also should say that using life cycle costing has to be the most appropriate method to assess project costs. We're going from cradle to grave now. We're not thinking install and get something running and then pass all the other costs on to somebody else. We have to consider optimum material choices, not just cheapest material choice. And we have to think and design with longevity in mind. So I would argue that the fit and forget slogan is what we should always have at the front of our minds. So in conclusion, we must all together take key steps to create long-term hard protection for our coastlines, for our coastal cities, and to guard against the increasing frequency of extreme events And many of our major cities around the world have seen these and experienced these, and they're not good. We need to protect our trade flows. We need to think about materials that will have at least 100 years of service life. We have to remember, if you have to go in and refit a hard installation, a hard sea barrier, when climate change is worse than it is today, that's going to be an impossible task and will undoubtedly result in loss of life. And would we be really happy with ourselves if we were being forced to make those decisions? And I would equally argue that stainless steel do offer the lowest life cycle cost of all materials when you're thinking coastal infrastructure applications, because there's a lot of unpleasant conditions there, and stainless steels will protect against those challenging environments. But it is all about correctly specifying the material grades. There's broadly 100 different stainless steels out there. It's not just one material. We have to choose the right grade for the right application and the right product forms too. So I would like to thank everybody for their attention, and now just sort of go to Joe and see if we have any immediate questions.
Yes, we already had questions during the session. Thank you, Tim.
Okay.
If you could go back to slide 27 on the Bayonne Breakwater. On that particular slide, you pointed that duplex was used for the rebar for the concrete slab. Was the duplex also used for the anchors underneath the slabs?
I believe it was. I believe it was a full use of sort of anchor bolts and rebar, but I can check that. I guess we've got the name of the questioner.
Yes, we do.
Yeah, so I can check that and respond by email if that's okay.
So we'll double check and get back to that question later.
We'll go back to the reference case.
Yeah. And then the next question was about the Miyako city case, so the lock case. And how was the overall weight reduction achieved, it asked, for these lock gates?
So it was a different structural design, which I don't have the detail of, but again, I can find that out and get back to whoever's posed the question.
Okay,
so it'll be primarily the internal design of these things, where the bulk, I mean, the obvious things are with a much higher strength material, you go thinner, but the internal design as well will be an important component of it. So I'll get the detail of that.
Okay.
Yeah, we can do that.
And then the next question is this. It says, is it now accepted that a PRE of 22, it is just below 316, is adequate for concrete in seawater? Does it assume a specific cover?
A specific
cover, so will be the concrete cover.
Yes, well, there are calculations that I don't have to hand for the amount of concrete cover that is needed, because you're not going to stop chloride ingress through the concrete. But what you will truly stop is the fact that the reinforcing bar will not rust. Therefore, you will not get a volumetric expansion, and the concrete will not crack and fall away. So there are calculations for the cover. I can get those and supply that information if somebody is specifically wanting that. But you have to realise when considering these structures that the reinforcing bar brings part of the ability of the structure to withstand whatever forces it's subjected to. So if you opt for a higher strength material as for the reinforcing bar, you don't need as much concrete to provide the same combined level of protection against the forces that the structure will be subjected to. But equally, you've got to think into the future, because in this sort of case, the forces that exist today will not be the forces that exist in 80 years' time. They'll be much higher. So some projection has to be necessary when designing things with longevity in mind, some future protection. But I'll get the calculation, and again, we'll provide that.
Okay. And then there is a more general question that I think it needs to be thought about. By using stainless steel, can we stop the sea level rise?
No, no, we can only protect for longer without having to go in and repair. So the clear notion of using stainless steel is that the protection we put in will require very little maintenance because it won't degrade or corrode. The sea level rises are coming, and it will take some time to slow that down because we are still heavily reliant on fossil fuels. So we know we're on a path that is going to be slow to change. Given that almost 40% of our people globally live within 100 kilometers of a coast, and with mass urbanization over the next 30 years, that proportion will get bigger. If we don't protect our coastlines, then those urban settings will disappear, and the industries that come with them and the surrounding land on which we grow crops. So if we can put protection in fairly soon that will survive for at least 100 years with minimal maintenance, then we're not being asked to go and rebuild or repair things when the sea level rises are more extreme, the events, the really sort of extreme events like tsunamis are not getting worse. There will be a period where things get worse from a sea level rise before they can get better. And maybe we can't turn the clock back fully ever. We will have to exist with an increased sea level rise. These are all things that are not fully known yet. But unless we can create more wetlands and areas to gradually absorb more seawater and act as sponges, and that's something we need to do rather than build concrete where water just runs off. We will never turn this thing around.
Okay, there's somebody wanting more information on the Miyako city coastal defense, so we will get that to him.
Yeah, we can get that case and send that out. That's absolutely fine. Yeah.
And then there's somebody asking what kind of surface treatment, so surface activation and painting specification is specifically needed for these coastal areas.
So painting of the structures. Yeah. That's a good question. I don't know the answer to that. I mean, I would argue there are coatings you can certainly put on concrete that claim to reduce chloride ingress and things like that. But it's not my field of expertise. But we will check that out and come back with an answer.
Okay, very good. There is a question coming up.
Okay.
It says you provided some examples using long products. What about flat products?
Okay. So there is no doubt that long products have been quite dominant in coastal defences. But if you think to the Japanese example with the floodgates, that is a very classic use today of flat products, because this is thin plate that is used primarily for the structure, and a large proportion of that lock gate is made from flat products. So where you're looking at features like that, it is very much flat products heavy in terms of the consumption. But you're right, predominantly long products is used particularly in the invisible parts and for things like gabions and meshes. It's mainly long products, but there are increasing opportunities for flat products. Equally, there are inquiries coming in now for repair sections, particularly at ports, where piling plates are being considered in stainless in order to assist with the port work on a faster basis, just because the costs of running a port and not having ships' berths in action is extremely expensive and detrimental. So it looks like there are more opportunities creeping in for flat products in this world.
Okay. There's another question coming up.
Sure.
What is the expected lifespan for stainless mesh on cliffs? Surely there will be some erosion.
You're bound to get some erosion, but choosing the right material with the right strength will limit the erosion. I don't think we have a definitive example yet that says it will last 125 years. But I think with the right specified wire thickness, we would certainly be comfortable saying 100 years is definitely achievable. But the amount of erosion compared to what you've got to recognize is there are two mechanisms. If you've only got a thin protective layer, that will be eroded away very quickly. And then the substrate material that will corrode even faster. So surface protection has its weaknesses where erosion is present. If you've got something where you take away the corrosion mechanism because you've got a material that doesn't corrode and you're only left with erosion, which is not going to affect stainless as fast as it affects protective layers, you have a different beneficial approach. So the material is naturally more resilient.
Okay, another question coming up. Come in now.
Good.
Are there any projects considered to eliminate concrete altogether and replace them by stainless steel structures?
That's a brilliant question. That would be a wonderful situation. I mean, concrete is probably the most polluting industry, contributing about 9% of total global greenhouse gases today. That's concrete and cement. But equally, concrete is such a versatile material, particularly where compressive stresses are commonplace. It has many, many advantages. So I think the notion of eliminating concrete would be fantastic, but it will take some years of development to get to that point. There are some wonderful examples of stainless steel structures made completely of stainless, no concrete at all, but they don't tend to be in coastal defense applications. So I think for some time we can see that concrete will be around and it has its place. But if we use stainless, we can reduce the amount of concrete. So I think stainless is one step on the right road, but there will have to be other developments, and maybe some kind of composite materials will ultimately start to replace the concrete. But we've got to decarbonize first. That's probably the more compelling requirement.
Yeah. I think we can take one more question.
We can.
Are you trying to explain those issues to administrations like the ministries of transport? Because it's those stakeholders that will pay for it.
The simple answer is yes. And what's really interesting, and I'll give a live example. So last year I did a webinar on corrosion, and attending that webinar was a senior member of the Department of Transport in the state of Florida in the USA. And that gentleman, once the video was put to YouTube, made his whole department watch the video first and foremost, and then asked me to come and do a private webinar to their team on the use of stainless steel in coastal infrastructure. So that was roads, bridges, sea defences, the whole thing, because they had seen the potential of stainless but didn't know enough about where and how to use it. So getting to these people is really important. I absolutely agree with it, but switching them on so that they want to be excited by the possibilities with stainless is a more challenging process. But once you've got them switched on, they tend to stay switched on, as long as you keep contact with them and keep the support going. Some countries are learning faster than others. Some people are still a little reluctant to try something new or think outside of the box. There is no doubt the jump to stainless is not natural for everybody, but we have to keep going, and the administration's absolutely right, are a key to this, unlocking this process.
Okay. Yeah. It's 4 o'clock, but I think we can take one more question, can't we?
Yeah, we can.
Are there any case studies available for protection of coastlines?
I mean, we have a number of case studies for protection of parts of coastlines. It depends how big you want to go with coastlines. So there are, yes, a number of case studies available. A lot of them are associated with coastline repairs and a lot associated with coastal towns and cities where stainless has been used. But they are good examples, they're solid examples, and the benefits have been seen by the users very quickly. So the simple answer is yes. If we have some in our library of available things, we're generally happy to share those cases, because building the knowledge and the understanding is really important.
Okay, thank you, Tim. I think that was all of the questions. So we can probably close the webinar now.
Okay.
And I'll hand back over to you.
Yes, well, thank you everybody for your questions. Thank you for your attendance. As I said, if there are any other questions that you want to pitch, please do so. You'll have my email address when you get the presentation if you've not noted it already. Have a good rest of the day, stay safe, and hopefully you'll join one of our next webinars coming up. Our next one is next month, looking at stainless steel frames for electric buses in urban environments. And then we're on to stainless steel with the hydrogen economy and particularly mobility in March. So some exciting topics coming up over the next couple of months. Thank you and goodbye.